All right, good morning, everyone. Welcome to the mobile track of the At Scale conference. My name is Nick Schrock, and I work at Facebook. I work on teams that build frameworks and abstraction that power our mobile experiences. What we're here today to discuss are the technical challenges of building on mobile. And really nothing is more important in consumer technology today. You know, it's often said that mobile is taking over the world, and at this point it might feel like a cliche, but like many cliches, it actually turns out to be true. So we now live in a world where nearly a quarter of the world's population, 2 billion people, that's actually over a quarter, have access to smartphones. And these smartphones a generation ago would have been considered magic. From this small device on your person, you have access to the world's information. You can contact all the people in your life. You can take pictures and do a host of capabilities enabled by people like us in this room. The shift to mobile is really the largest shift in computer technology since the spread of the internet. And it's actually one of the biggest explosions of innovation ever. What's awesome about it is that all of you can build for these devices and do so anywhere in the world. You have access to unparalleled distribution channels through the App Store and the Play Store. 2 billion people at one click can download your software and execute it on one of these magical devices. Once you actually make something that people want, you can also grow it at unprecedented speed through online communities like Facebook, Twitter, and others. The net result of this is that software engineers really have never been so empowered. And the opportunity before you is almost limitless. But with this unprecedented opportunity actually comes a really challenging technical landscape that's pretty new, and it's really hard. Customers are demanding native experiences, and they're actually they're voting with their feet. So if you look at this slide, this is time spent on mobile devices across iOS and Android. And what you notice about it is that only 14% of time spent is in the browser. Actually, 17% of time is spent in the Facebook app, 10% in messaging, 32% in gaming, and other apps as well. And generally, native experiences dominate these other categories. These usage of native applications is just dramatically outstripping web-based applications, and it has no sign of abating. Even on a single platform, developing for these native apps is actually really difficult. The apps are generally long-lived and highly stateful. They're often required to be multi-threaded. You're operating in constrained environments with limited processing power, limited battery, and on devices where you don't control the entire ecosystem. Other applications are executing in this environment. You have a less agile deployment model than in the web-based past. You have to deal with multiple outstanding versions of your application in production at any one time. And lastly, on Android, you're dealing with an incredibly fragmented ecosystem, as we'll hear about later. You're dealing with an extremely wide variety of devices and device capabilities, and also a very wide variety of iOS versions. So I mentioned Android specifically. And the story of Android, especially over the last few years, is a really remarkable one. Essentially, in the last 2 years, the Google Android user base has grown from 400 million users to 1.2 billion users. Especially given the fact that this is a hardware platform, that is amazing and remarkable. Put another way, Android now has twice as many users as iOS. However, iOS is clearly still a relevant platform. It's technically interesting, they have great user experiences, and they also do very well among high-end users and in the developed world. So this means that you can extrapolate from the App Store numbers that Google and Apple publish that the iOS average revenue per user is actually 4x higher than iOS. So net result, you get half the users, but double the total revenue. But keep in mind, Android is growing faster. The net result of this is that it's critically important for any consumer technology company to target both platforms. So really what this track is about, it's about harnessing this opportunity that has been presented to you, which again is really unprecedented, and doing so by addressing this technical challenging landscape that it presents to you. So what are we going to talk about today? This is the agenda as we go through this schedule. And note that all of these talks are in this room. So if you don't have to go to the bathroom, don't need a refreshment, you can just hang out in here. At 11, we'll hear from Facebook about their iOS architecture. This is about their proprietary persistence stack and our new kind of functional style for doing declarative UIs. We'll talk about cross-platform development at LinkedIn. Then we break for lunch for an hour at 1. At 2, we're back in this room for 3 lightning talks from LinkedIn, from Facebook, and from Uber. 3 o'clock, we'll actually hear about Microsoft's approach to cross-platform development. And finally, from Facebook, we'll talk about the challenges of targeting emerging Android. One more additional note, there's actually a mobile group on Facebook where we will post all of the talks and also answer any questions that come up. And with that, I'm going to hand this off to Adam Ernst, and he's going to talk about Facebook's persistence stack. Thank you.
Hi, everyone. I'm Adam Ernst, and I work out of Facebook's New York City office on the iPhone feed team. So I'm really excited to be out here today to talk to you about how we totally overhauled the model layer in the Facebook iPhone app and why we did it. Today, I'm going to tell you about a better way to build mobile apps, one that we applied in the Facebook app. And first, I'm going to talk about the model layer, and then one of my colleagues is going to talk about the view layer. So these are some hard-earned lessons, and it varies depending on what your app does, whether these lessons will exactly apply to what you do. But I definitely think it has wide applicability to a lot of different apps and is really exciting. So first, let me take you back to 2 years ago, when, as Jay mentioned this morning, we were kind of making this mobile shift at Facebook, going to building mobile first. And 2 years ago, we were actually porting all of our apps to native code, so that instead of being written in HTML5, we would write different features in native code for each platform. So our first project was to rewrite the Facebook newsfeed in native code, switching away from HTML5. And this project was a huge success. After we shipped it, newsfeed was over twice as fast, right? Big win. But obviously, we wanted to bring that same speed boost to other parts of the app. So the next version, we ported timeline to native code, and then we ported groups to native code in the next release. Next version of the app, pages and search and so forth. But we started to notice we had a big problem. With every version of the app, even though we weren't touching newsfeed, we were just porting other features to native code. Newsfeed got slower and slower and slower. And this is a big problem, right? Because newsfeed is the heart of the Facebook experience. If you're using Facebook, newsfeed is the #1 thing you care about. So we did some digging. We wanted to find out what's going on here. Why is the app getting slower? And it turns out the problem was in the model layer. I'll get into why in a minute. But it boils down to this. The biggest mistake we made when rewriting the app in native code was actually choosing to use Apple's core data framework as our object caching layer. So a quick detour to tell you what I mean by object cache, right? Like most apps, including probably most of yours, I remember I was listening to Brett Taylor this morning talking about Quip too, where he was like, the server is the source of truth, right? You have a local cache, but it's just a cache. The server is the source of truth. So that's true for Facebook as well. We primarily show data you download from a server. And what are the 2 properties we want for that cache? Number 1, well, obviously we want to cache objects. We want to be able to save them to disk so that if you restart the app, we can show you that data again without having to hit the network, because that's slow. And we want a way to keep cached objects consistent. Let me tell you what that means. So let's say you have the same feed story on News Feed in the Facebook app and on someone's timeline. And if you're a user and you hit like on that story on timeline, and then you navigate back to feed, you sure expect that it's also going to show that same state on News Feed. So you need to keep those objects consistent between those two different views. So that's what I mean by consistency. So for those of you that aren't iOS developers or aren't developers at all, what is Core Data? What is this Apple Core Data framework I mentioned? It's Apple's built-in framework on iOS that does object graph management, is what they call it. Kind of similar to an ORM, which is an object relational mapper, which maps database entities onto object-oriented language objects. But it's a little less emphasized on the relational concept and a little more on just keeping your graph of objects. So under the hood, Apple's Core Data can be powered by SQLite or various other back-end frameworks. We used it with SQLite. And so what's the matter with Core Data, right? Core Data is a fine framework. It does what it professes to do. What are the problems that we saw when we tried to use it in the Facebook app and scale it up? I'm going to break those into three main areas. Number one, for large, complex apps, Core Data is too slow to set up. This is a huge problem for us. Number two, even when we did get Core Data finally set up, which required all kinds of crazy hacks, it's too slow at runtime. There's a runtime performance penalty that we didn't want to pay for the Facebook app. And finally, even if it weren't slow, Core Data sticks us with a programming model that we don't like, because it doesn't scale well to having a large number of engineers working on the same product. So I'm going to drill into the first one first quickly, which is setup. This is a graph that kind of shows the general trend of how long it took to initialize the Core Data database in the Facebook app. And this is absolutely crazy, right? We had all these problems where you'd start up the Facebook app for the first time, and you'd stare at a spinner for like 30 seconds. And why is that? Like I mentioned, we were porting each new feature to native code. And that would add a roughly linear number of new types to the Core Data schema, the number of object types. But it turns out that the number of relationships between those types would grow at a quadratic or even faster rate. And the way Core Data works with SQLite is that it creates a database table for every type and either an index or an entire table for every relationship. So we'd end up booting up the app and then spending all this time setting up this humongous SQLite database on the phone. And we did all these kind of crazy creative hacks, like shipping a pre-built database file with the app and then just copying that when we wanted to set up the database. But even that is slow, right? So we really don't want to have ourselves forced into having one monolithic object store. And Core Data really encourages that. In fact, it makes it really difficult to avoid that. What we really want is many small distinct caches, one for each product, so that it isn't too expensive to set up each store. But this is pretty crucial. We still want consistency between all those different caches, right? If we go back to that example of News Feed and Timeline and the stories, those might be separate caches, but we still need to have consistency between them. So in a bit, I'll get into how we tackle that problem. So that covers the setup performance problem, but then we have a runtime performance problem. Even once we get past that extremely high cost of setting up that Core Data database, we still had issues. There were some aspects of Core Data's design that didn't suit what we needed. One of those, ideally, is that we would have something like this in the Facebook app, right? There are all these different products. They each are processing data from the network or from wherever they get it, and they're independent of each other. They may asynchronously communicate with one another to say, hey, I got this data from the network, or hey, the user entered this data, but they don't block each other. Unfortunately, Core Data looks something more like this. There is a global persistent store. And anytime any of the products wants to actually process some new data, it has to acquire this global persistent store lock and do that. This means that if News Feed downloads some data, it's going to block every other part of the app. So we ended up with these really big app-wide stalls where the entire app would kind of freeze up for a while because Timeline would be trying to read some data and News Feed was busy processing data. For those of you that are Core Data nerds, by the way, we tried all kinds of solutions, parent-child contexts, many small managed object contexts that are created on the fly. Each one has its own trade-offs. If you do have any questions, I'm happy to talk about Core Data after this. I'll go into as much detail as you like. Crazy times. Core Data also has this feature that's problematic for runtime performance called faulting. The idea here is that with any object graph management solution, you have to think about what you want in memory and what you don't want in memory at any given time. Now, Core Data wants to do the simplest thing, which is to say, as a developer, you don't have to worry about it. We'll take care of it. So here's an example, right? You might have a comment object in memory, but the author of that comment, a person, is not in memory. So Core Data will say, all right, I'm just going to give you a fake author object, and then if you actually try to read from that author object, I will block the calling thread. I'll go off to disk, read in all that data, and then return to you. So for the longest time, we had this problem in the Facebook app where when you'd scroll through comments, we'd have this huge stutter, frame drops, every time you scrolled a new comment into view, because we were going to disk to load all that information and then return it to you. And Core Data does have some techniques to allow you to get around this problem, like it allows you to say, hey, anytime I load a comment, I want you to prefetch the author, which is great. But in the end, it didn't live up to the promise of letting you not worry about which data is in memory and which is not. So we would prefer to have a solution where you don't have any magic. You have to explicitly say, all right, I want to load this in memory, and it stays in memory, and then let it go yourself. The final problem is that even if its performance were excellent, it still has a programming model we don't particularly like. Now, the model's pretty similar to most other ORMs out there, so it's not so much that Core Data made some bad choices or some unusual choices. It's that we want to make some unusual choices to get a model that we like more. And the number one choice Core Data made was mutable models, right? This means that if you have a person object, you can call person.name equals some other name and change it at any point in your program's execution. It's a pretty common choice. But it also means that it's hard to reason about the code. If any part of the code can change stuff, you have these problems with random classes deep inside your hierarchies, mutating the models when you don't expect it. It's hard to audit for where changes are occurring. So we kind of want to avoid that. And models being mutable also means that they're thread-defined. You can't just pass a model object to a background thread. Instead, you have to actually grab the object's identifier, pass that to the thread, load it up from a different store in the background. It gets to be a lot of hassle when all we want to do is quickly pass those objects between different contexts. Finally, mutable models encourage two-way bindings. That is, if you're an iOS developer, you know it's probably key value observing is the name it's called by on iOS. But in general, this concept of like, all right, I have a model object. I'm going to listen for changes to each of the properties on that model and then update my UI. This seems like a really simple thing, and it works great for small projects. I used it all the time before joining Facebook. But when your app gets larger and larger and more complex, and especially when you have lots of developers working on the same product, you end up with these huge chains of updates that are just really hard to follow or debug. Because often these bindings are hidden in different parts of the code. You can't really get an overall visualization from the top of what all these bindings are and how they're interacting. So it made it really hard to reason about race conditions and cycles. So if we take a step back, some of you might be familiar with ACID, which is a set of properties that we expect of relational databases. So it turns out that for an object cache, we don't need all of ACID if we're just caching objects that live on the server as server truth. So which do we need? Atomicity, yeah, we want that. If we make multiple changes, they should all occur, or none of them should occur. Consistency is an interesting one, right? So for a bank, if you're a bank, you definitely want all of your schema to be consistent at all times. If you take $15 out of my account and put it into your account, there better not be some intermediate state where like things are not consistent. But for the Facebook app, you go back to that newsfeed and timeline example I gave you with the same story. It's OK if they're out of sync for a few milliseconds, right? That's not the end of the world. So it turns out that we do want consistency, but it's OK if it's asynchronous and deferred, as long as and that helps us to avoid those kind of massive stalls where there's this big bottleneck in a centralized lock. Isolation, we do want that. And then durability is also, I think, one of the really interesting ones. It's just a cache. If for some reason the app crashes and we lose a few of those cached stories from your newsfeed, that's OK. We'll just reload them from the server. We certainly want to make a best effort at being durable against storage failures. But again, Facebook is not a bank. It's OK if on the client, as an object client-side cache, we lose a few things here and there, if it helps us get better performance. So we decided to start fresh, and we came up with this: a 100% immutable object model framework. And we undertook this huge project to port newsfeed to it, which is kind of crazy. It's kind of like you've got a skyscraper and people are building things on the top, right, adding new features to newsfeed. And meanwhile, here we are on the first floor. We're just like, all right, guys, we're just going to take all the girders out and like change everything underneath you. But it ended up working pretty OK. So there were some challenges along the way. Let me tell you about what immutable models are. It means they're deep immutable. So if you have an immutable story object, not only is that story immutable, but everything the story refers to is also immutable. And it also means there's no way to immediately mutate the model. We had a lot of developers ask, all right, but I really want the light count to change right this second on this model object. It's like, nope. The only way to change that is to change your thinking. You're going to flow an update through a top-level store that says, hey, I want to change this story, and then eventually it'll come through your code again. So let's look at how that works. So you have a story in your feed, simple little story here. And what you want to do is update that story because the user just tapped the like button. So you're going to have this update function that is passed to the store. And the store is actually going to copy that entire tree, make a brand new copy of that entire story, and then change it using some certain private methods that only it knows about so that the story actually has one like. So that's how it works on the individual object level. But what about those cross-product things like newsfeed and timeline? So we have an object called the consistency manager. And its job is to sit there and it does two things. One is that you can register with different parts of the app can register with the manager. So newsfeed might pass it a model object and say, hey, give me the new version of this model if anything changes in it after doing that tree copy. And the other job it has is that parts of the app pass data into the consistency manager as they get it. This is how it learns about new things that it needs to update those objects for. So for example, notifications might load some notification and realize that, oh, look, Ari changed his profile picture. And that means that we might have to update some of those newsfeed stories, so it'll go there and actually do the work to update those stories. This also means that there's no central component for persistence. Each part of the app writes whatever data it wants into disk, and some parts of the app don't write anything to disk at all, which is a huge win for us. For example, if you're showing a list of real-time feed stories about a sports game, those are going to be out of date 20 seconds after you downloaded them. There's no reason to write them out to disk. Core data forces you to write everything to disk and keep it there almost indefinitely, which is a big problem for us. We did do one optimization. We wrote our own NSCoder subclass that uses message pack instead of using Apple's built-in NSKeyed archiver. That was way faster. We give up some of Core Data's features like object uniquing. Under Core Data, if you have 3 references to Ari, it's always the same object. In the immutable model frameworks, you can actually have 3 different objects for Ari. And they may even have inconsistent state because, like I mentioned, we have deferred consistency. The number one objection we got was, how do I know what changed? The key here is to stop thinking in terms of deltas or bindings. Instead, think of, I get some properties, some state from my parent. And then I'm going to do whatever computations I need and then pass that to my children. That's the key way you think about how model objects get passed around in this new framework. And the other is that you have to make the user interface efficient at doing nothing if nothing has changed. Ari will get into a lot of detail about that shortly. We also code generate all of our models based on a server schema. We tried to, at first, doing this like handwriting like these, and that was just a nightmare. So no magical features. We don't really want to avoid all that crazy faulting magic, like I mentioned. And finally, we generate them using custom framework templates that we use with ModeGenerator. So what were the results? The biggest one, and the most important one for us, better performance. It's 35% faster to load newsfeed when we finished porting newsfeed to this immutable model framework. And more importantly, it no longer got slower with every other feature that we ported, because now we had distinct caches that didn't have those big app-wide bottlenecks. Second, getting rid of those bottlenecks, like I mentioned, means that you can port as many other features as you want. We didn't have to worry about slowing down other parts of the app. We had asynchronous deferred consistency, which let us do that. But a really big thing for me as a developer, it was a better programming model. It was easier to understand the code, easier to follow state flowing through the system. You didn't have those big chains of updates that were rippling through with all those two-way bindings. So that meant fewer errors, easier to test. And I got to say, this got us thinking. All right, so we did this for the model layer, and that was really great. What if we also applied it to other parts of the app, like the view layer? And so now I'd like to introduce my colleague, Ari Grant. He's going to talk about the ways that we applied these lessons to the view layer of the Facebook app. Ari?
Thanks, Adam. So yeah, so I'm basically going to go through the exact same presentation, but replace the word model with view. No, I'm just kidding. All right, so I'm here to talk about a project we did called Components, which is a project we basically took on to take the same type of patterns and lessons and apply them to the view layer. So here's a high level of what we're going to go over. So newsfeed has a lot of constraints. And 2 years ago, as Adam and Jay said, we started to rewrite it using native technologies. And over the last 2 years, the number of constraints has grown. And just like Adam showed you, the complexity increased over time, and it became more and more brittle. And so basically one day, after doing this, after doing all the model work, Adam said, we woke up and said, all right, enough of this. This is terrible. This is too complex. We're going to move all of the complexity into the infrastructure. And so we spent some time designing a new framework. And through this, a project called Components was born. So again, going back 2 years ago, when we said we were going to basically build native apps using the native SDKs. We were using HTML5 and other web technologies at the time. And so we decided to rewrite the apps. We asked ourselves, what kind of architecture do we want to use? And so we choose the standard one that Apple suggests, MVC. And a lot of people have different opinions on the details of MVC, but we all agree on a high level it looks something like this. It says you break your app up into 3 main pieces. The model, which contains the state and the data. The views, which are how you present it to the user and how they interact with it. And a controller who mediates between the two. And the model and the view don't interact directly, and this is how you get your separation of concerns. So the first question we had to ask was, how do we take this pattern and apply it to newsfeed? So on the right is an example newsfeed. And on the left is a rough skeleton of what the view hierarchy might look like. So at the top level, we have the feed view, which would map to this entire view and all of its subviews. Then we're going to have a set of story views for each story and feed. And each of these are going to have a set of subviews, like for the likes and comments and photos and videos and so forth. So the way we're going to build the view here is pretty straightforward. So next question we had to ask was, what might the controller look like? So one way to do it would be this, which is actually a terrible idea, right? One controller doing everything. So instead we decided to actually build a hierarchy of controllers. So the feed controller had a story controller for each story and feed. And each story controller had like controllers, comment controllers, and a set of controllers below. And then the mapping, again, is pretty clear of how the controllers interact with the view. So they each can talk to theirs. So this is the basic setup we chose of how MVC was going to look in our infrastructure and in our app. So the first question we want to ask is, OK, so what does it look like when you receive a model? And this is independent of whether it was using the core data like Adam described or mem models. So the model store would pass in a model to the top-level feed controller. And it would decide, OK, which story controller are we going to pass this to? And it would configure the controller, or the controller would configure itself. Then the story controller similarly would take some of that data or properties and configure its subcontrollers. Come on. There we go. And then at any point during this, these controllers would configure their views. And so you have the data flowing from the top downward. But if only it were that simple. As Adam said, on a story, you might have the author, and they have a profile picture. And so the story's author's profile picture might change. And so we ended up realizing that you end up needing these subcontrollers to actually register to listen for updates on their views as well. If that's not enough arrows, we'll add a few more. So what happens when you tap on the like button? So you tap on it, and a tap message is going to go from the like view to its controller. And so then maybe the like controller, in a simplified example, would mutate the model saying does like equals true. Even in the mem models version Adam described, where we don't actually mutate the model, it would say to the store, I would like this change. But then the like controller might have to invalidate its size, for instance. Maybe now it shows the number of counts and it got taller. So it has to say upward, oh, hey, my size is invalid. And similarly, the story controller might try to tell the feed controller, my size is invalid. And then, of course, either of those happening could also tell the model store that change has occurred. But if that's not enough arrows, I can add a few more. The interesting thing, of course, is you can tap on stories to open them in the view where you see the story alone. Or there's also actions that the feed view can do. And so you end up with tons and tons of errors and arrows. And so I actually found this to be a disaster. Right? So data and events are flowing all over the place. And you'd literally sometimes see engineers just put their heads down and go, I cannot figure out what's going on, because stuff was flowing all over the place. And not only that, it was doing it across multiple threads. Right? Because again, we want to have caches, we want to have data propagating different ways, everything is mutable, and you want to offload some of the work onto other threads. So we had the question of how can we do this? The first approach would be to do everything on the main UI thread, which is actually a terrible idea. Because on a 60 hertz device, that gives you 17 milliseconds for an event to be processed, or you're going to drop a frame. And so when you have text layout, so for instance in Thai, a screen of text can take 12 milliseconds to lay out. You really just don't have time. So that wasn't a good idea. So we said, OK, what if we make everything atomic? Well, now you at least know that setting properties individually are safe, but it's still, you can't guarantee that the logic from a top level is correct. And so you have races galore. So the third option would be to use shared locks to actually serialize the sections that mutate or cache data to ensure it's in order and not racing. But now it's really complex to reason about the flow of data, and deadlocks are incredibly easy to now occur. And so really looking at this, what we realized was it's really difficult to deal with mutable state across multiple threads. It's just really hard. And we had tons and tons of bugs. Here's a real bug we had. So this is a story that had 0 comments. A new story came in from the server, now that's saying it had 2 comments. So the story re-rendered. You can actually see the story is correctly taller inside of the box. But the new height has not yet arrived. It's not clear if we're waiting on it from some background thread to punt back over to the main thread. Maybe it got lost in the wilderness of data races smashing over each other. But all you know is for some amount of time, a person using the app can't even tap the like button. And us being Facebook, tapping the like button is something we care about quite a bit. So how could you solve this? Well, at first we said, OK, clearly this is really difficult. Let's just write a bunch of tests. OK, tests are good. Everyone loves tests. So what are we going to test? We've got to make sure that the views are configured correctly, that height changes propagate, any kind of state that we want to adopt is handled correctly, and that you recycle views. And it's actually the point of recycling views where we said, holy crap, there's way too many combinations. Recycling views is the idea of when a view goes off screen, we don't want to deallocate it. We want to keep them around so that later we can try to reuse them. But when you look at the number of types of views we have, and you want any of them to be reconfigured into any of the others, the number of possible permutations here just explodes. So it's hard to say this, but in this case, testing was not going to fix it. So we worked hard, and we came up with an entirely new solution we called components. And it looks like this. This is a simplified version of actual code from our code base for how we render the feed story. And so basically, it's a description of what we want the views to look like, and that's it. So I say I have a stack, which means you want to put a bunch of views together vertically, stretch them horizontally to fill the view, put spacing in between each, and then I want to stack things like the header that contains the profile picture, the message that has the text of what the post contains, the like and comment buttons, and all the other parts of feed. And we replaced everything with this. If only that we were done at this point. There was a lot we had to do first to get there. So let's look at what the system we were dealing with actually looked like. Luckily, it wasn't as bad as core data. So on iOS, they come with a built-in view API. It's a hierarchical tree structure, which is pretty common in most UI kits. Similar to the DOM. You can mutate the tree. You add subviews, you remove subviews, you reconfigure them. You override a method to determine the view size. You override and determine the layout. And all of it can only be used on the main thread. This is where we started. And if you look at this, we already just said my favorite word, mutability. And so we started off and we said, OK, can we do better than that and just not have mutability? You also saw layout and sizing. It's something that every developer has to write for every view, which basically means you have to do math. And so we said, what if you just don't do math? This is not advice for your general education, but when it came to newsfeed, this was a great goal. And so the way we avoided doing math was we basically took Flexbox, which is a web standard basically from CSS, and chose to adopt it. It's a description of how you want your views to be laid out relative to one another. You describe it, and then you're done. The layout system will figure it out. And so it is flexible enough to allow you to specify things like this. You can align things to the left, to the right, or if it's a vertical stack, top and bottom, specify where the space goes, and that's it. And we actually found that with horizontal and vertical stacks alone, that was enough to describe most of our feed. So we kind of took all of that together, and we set up the initial goals for this project. The one-sentence version is we wanted to take all of the really complex behavior and calculations and move them to the infrastructure, making it really easy to deal with views, both for layout and recycling. We wanted a one-way data flow. I'm sure you're already missing that graph with all those arrows. We wanted to make composition the only way to go, and that everything would be immutable. And so again, by moving all this to the infrastructure, make the worst possible errors like that layout bug I showed you impossible. And then finally, we wanted to make any asynchronous computation like text layout or image decoding and make it invisible, and you not have to worry about which thread it happens on and how that data gets back to the main thread. And so we came up with a project. I'm sure you have no idea what it's called, so I'll tell you. We called it Components, which was basically a direct port of some of the concepts of React to Objective-C with some C++ mixed in to avoid a few square brackets that Objective-C loves. And so basically what the system is, it's a pure function that takes in the model and produces a description of the views you want. The infrastructure calls this, and there's your views. If anything changes, it's a pure function. The infrastructure calls it again and updates the views. Because it's a pure function that just takes immutable data and produces an immutable description, you can call on any thread, you can size on any thread, and there's tons of different layouts. Like I told you, we use Flexbox out of the box, and then you can build your own layout as well. So here's basically what the pipeline looks like. So take the story mem model. So these are, again, the mem models Adam talked about. And it goes through into a component and then into the view. This looks a lot like MVC. You have the model and the view with a component in the middle. But remember, it's just a pure function. And so it looks like this. There we go. So first you start with like a story model. The developer is going to write the pure function that turns that into a component tree, a description of what the view should look like, which the infrastructure, the red wall here, then takes and turns into the correct view hierarchy. And the nice thing about this graph, or this depiction, is that all of the arrows point to the right. It's one-way data flow. It's a much simpler system. Just to contrast that with the old system, remember this. So we found this really cool trick. If we took the old system and we simply renamed the controllers to components, we could do this. It's a pretty cool effect. Now, if you notice, there's no arrows connecting the components to the views at all. So you as a developer can forget they even exist. And now you have a much, much simpler picture. Let's look at it another way, stacked vertically. So what happens when you actually do a like? So the like components can now tell the store, hey, change this model. I want does like to be true. And now the store will produce an entirely new component tree. I'm sorry, your function will produce an entirely new component tree, which will be used to generate the views, and then you're done. No mutability, no worrying about keeping track of state. It just reruns your function. You might be thinking, though, this is really expensive then. If it's going to spin all these up and there's going to be a bunch more views, how do you actually even remotely keep this cheap? And the way we do this is through view recycling. So imagine this made-up hierarchy of views, which might look like this actually in the feed. This is a simplified version. And so then imagine via a model change, and this could be the story changed, or you actually want to reuse a set of views for an entirely new model somewhere else in feed, we treat them both the same. So imagine we want to convert this view into this view. So I emphasize the video in red because it's a fundamental change to the hierarchy. But we can assume that the other three have different properties. So what we do is we basically say, OK, the entire set of views is eligible to be used for this tree. And so we basically start at the top. And we say, OK, I need a card image. And we look at the set of views we're trying to reuse. And we say, oh, there's a card image. So we use it. Then we go to the next child, the image for this profile picture. And we say, oh, there's one available. So we reuse it and configure it with a new image. Same for the label. We say we need a label. And then we reconfigure it. And then finally, when we get to the video, there's a number of things that can happen, but they're all basically private. So for this text box, we don't need it now. It's going to be unused. We could hide it. We could throw it away. We could put it into a shared reuse pool. Whatever, it doesn't matter. This is completely in the infrastructure, so it's like it never existed. And then, again, we need a video view. So this could come from a shared pool. It could be allocated on the fly. Again, it doesn't matter where it comes from. All of this is done by the infrastructure. And so by doing view configuration this way from the top down, it's actually ON in the size of the tree. So we're not doing a full tree diff algorithm, which is much more costly. We're just walking down and finding views to reuse. But again, this is all in the infrastructure. You just deal with components. So as far as you're concerned, views don't exist. Components is the way you talk about them, and components are immutable. So you get to live in a world as if you had immutable views, which is a pretty cool thing to have. And the way we do this is by specifying them through a configuration. So here's an example configuration for an image. It's enough curly braces and square brackets to at least make a Lisp lover happy. But so here we want an image view, right? And so we basically specify set image, here's the image we want. Set content mode, which is how it's going to stretch or scale if the image has a different aspect ratio than the view, and you're done. So we're specifying to the infrastructure, this is how I want the view to look. You're not creating a view, you're not configuring any of its state, you're just describing how you want it to look. So the infrastructure then can, using its recycling mechanism, apply this, making sure not to set any attributes that have already been set and minimizing the number of work done to the views. And the nice thing is this is declarative. You look at this and this is the state. You don't have to worry about where you're coming from, where you're going, setting the state yourself. You simply describe it. And again, these are immutable. So we used to have a lot of code that looks like this. The user taps the like button. You send the like request to the server. You mutate the model. You update the views. And then you say, hey, the layout's invalid. These are immutable. So you do none of that. All you have to say now is to tell the store, again, this is the mem model store Adam described, apply the like mutation to this story. And the infrastructure will rerun your function to produce the component tree, find the views to recycle, and put it on screen. So there's one question you might be wondering, which is, well, if everything is immutable, how do you actually have any state? So components are short-lived, right, because they're immutable. So this means anytime something changes, we're going to immediately create a new tree. So components can't have an immutable state because they don't stick around for very long. But if you actually create a new state object and we pass it into the next component tree that is created, then we can basically pass the state along from one to the next, which simulates them being long-lived. And you can think about a component as if it were always around. Just to make this a little more concrete, here's what the APIs we have look like. So this is the init method, which creates one of our components. And it just calls self.state, saying, give me my state. And then it passes in a lambda, or block as they're called in Objective-C, to create the state if it's not there the first time around. It's up to the infrastructure to make sure that you get the correct state. So that when you build up your component tree and you call this, we can make sure the state goes from one component to the next. And then similarly, you can mutate it or update it. So here we call the update state method. And you pass in a block that takes the current value, you produce the new value, and you're done. When someone creates a new component tree the next time around, which this actually does, it will get that new piece of state. So again, everything is immutable. But here you can actually have what appears to be a component modifying its state. So the last final remark I'll make is on the language we chose, which was Objective-C++. So Objective-C with a bit of a C++ on top. And we chose this because it has type and const safety. In Objective-C, you say I have an array, and you have no clue what's in it. So you could have an array of strings, but index 7 turns out to be a dictionary, and you have no way to know until runtime. Also, nil-safe collections. If you insert nil, which is Objective-C's equivalent of null, into an array in Objective-C, it just crashes at runtime, which is not a good behavior. And then it's also more efficient. So C++ has stack allocations, move semantics. It's much quicker and cheaper to look up a property on a class. Objective-C has runtime overhead. And also C++ has aggregate initialization, so you can do this. Structs with actually fields to specify. So if this, and here we're specifying layout parameters, has 20 parameters, you can specify just the ones you want. If this were Objective-C, you'd be specifying all of them. And so this is basically all of the pieces we put together to make our components infrastructure. And so we actually converted all of feed to this. And it's already out there, and we're ramping it up to everybody. And so what did we see? We got a much better programming model. Everything is immutable. Everything is much easier to reason about. And because it's declarative, we actually ended up with 70% less code by the time we rewrote all of feed, which is absurd. And also because the infrastructure owns all of applying attributes and recycling, it's very performant out of the box. And if we tune the infrastructure just a little bit, every single story in newsfeed benefits. And so just to remind you, to put this all together, what it looks like, this is it. This is a slimmed down version of our newsfeed component, saying stack these components. And some of those are stack these components. And then some of those are configure an image this way. So here's what a button looks like. We specify the images for what it looks like when it's normal and pressed down. We say whether or not it's selected, whether or not it's enabled, what action to use when you tap on it, and that's it. The infrastructure will go get it and get it cheaply. And so the mantra of all of this, in summary, is to say, don't make me do these really hard things. Don't make me configure things or deal with recycling, layout, who wants to do math? I mean, it's not calculus, but it's still a pain. And so instead, do it for me. And so you basically say to the infrastructure, this is the view hierarchy that I want, and then it makes it happen. Then you say to the infrastructure, this is the layout that I want, and then it makes it happen. And then you say, this is the state change that I want, and it makes it happen. And all of this is done in a declarative API. And so the only thing left then is, what's the future of components? So if you look at all of this together, components plus mem models, as Adam discussed, we've built a lot of stuff using these basically immutable objects and pure functions that generate them, which is very functional in nature. And we've applied this to the model, the controller, and the view of all of how we've built feed. And we took the best parts of Objective-C and the best parts of C++ together to pull this off. Luckily, Apple took those best parts as well and made a language called Swift that is functional out of the box. And so the next step for us that we're super excited to do is to port all of this code to Swift, be on the cutting edge, and make everything performant and awesome, providing the best experience on mobile that we can. Thanks.
All right. So that's the end of this part of the session. We will reconvene at 12:05. So you have about 8 minutes to get some refreshments. If you don't have, feel free to chill in here. If you don't have anything to do, introduce yourself to someone you don't know. Otherwise, we will see you in about 8 minutes. Thanks.